Hi, welcome back to the last part of the lectures on analog to digital conversion using the Atmel micros, okay? So what we're going to do is we're going to delve into some of the more detailed aspects of conversions. And first of all, we're going to look at the modes, okay? So here we've got the modes. We've got a single conversion mode and a free running mode, which means you have to kick it off to do a conversion and it will do a single conversion, or in the other case, you kick it off and it just keeps running consistently as fast as it can go to do conversions, okay? And we know that the speed of those conversions is based upon what we have set into this register here, these bits here, okay? This is our sampling rate. In addition to that, we can have it so that it will send an interrupt or trigger an interrupt when a conversion is complete. Okay, so it's doing a conversion, and every time it finishes this conversion, it will generate an interrupt. So we could have a single mode with an interrupt, okay, or we could have free running mode, and it's going to create an interrupt every time the ADC has finished a conversion. So it's just a single conversion and interrupt, or multiple interrupts after each conversion, okay? So that's how we can get it to trigger an interrupt. So let's have a look at some of the values in this ADC SRA register. ADN, okay, so ADN is our enable. Now we don't want to waste energy nowadays. We're right into maximizing the use of these microcontrollers. If we waste a tiny bit of energy, then we multiply that by millions and millions, because that's how many of our circuits are produced out there, okay? We want to avoid this. We want to increase the energy star rating of our devices. And so what we do is what the manufacturer has done here is given us a flag to say, hey, if you're not using the ADC, then all that part of the circuit inside the microcontroller will be turned off. And that means we're not wasting energy. So you only turn it on when you need it. If you're only going to do a conversion every 10 minutes, then just turn it on, do a conversion, then turn it off again, okay? That will really help you reduce your energy consumption. When we want to start a conversion, so if we're in single conversion mode, when we write this bit to 1, it starts a conversion, okay? Now in free running mode, writing this bit to 1 starts the first conversion, and it will just then continue to do its conversions. The really important thing here about the first conversion after ADSC has been written is normally going to take longer. It's going to take 25 clock cycles instead of the normal 13, okay? So it takes a little bit longer after ADSC has been written. ADC will be, now you can actually read this, and you can therefore use it as a flag in a way to see whether the conversion is complete, because it will read as one as long as a conversion is in progress. Now that sort of makes sense for a single conversion mode, because what you'd be doing then is you'd be kicking it off and starting this conversion, and then you would read this bit, and while it's 1, you know the conversion is still taking place, and when it has finished, you will you'll find that this is 0, and then you can do something with it. So that sort of helps you make sense of it. Now, auto trigger enable. Now this is when you want to trigger the ADC to do a conversion. So up here, I was talking about this modes where we're getting an interrupt when a conversion is complete. But this is when we want to do something that will cause an interrupt to take place. So we've got different features in the microcontroller that allow us to do things like set up a timer to do an analog to digital conversion. And indeed, one of the factorials, there are 3 factorials, I think, on ADCs, and the last one of those talks and shows about how a timer is used to create an analog to digital conversion. So this is, again, how we make an ADC do it. So we've really got another mode here in a way. We sort of can make our ADC do something automatically in software by doing a single conversion mode. And then we can have it cause an interrupt when it's finished, or we can have it consistently doing it. Although we can also have it triggered. So in the single conversion mode, we can cause it to be triggered by one of a number of different events. And if we just pop into the data sheet, we can have a look to see what are some of these modes that we could use. Okay, let's go to the data sheet. There we go. Starting a conversion. So here, having a look at this bit of a circuit here, we've got all these different sources. We've got ADSC can cause our conversion to start, right? Or we can have one of these other different sources, which are controlled by these 2 bits in a register, which cause it to do a conversion, okay? So this is how we might set it up. We can have it either under our own control and software, or under control of something else, some external source. So if we go down here, we might find what these are. In fact, I know they're in register B. So let's just have a look at register B. And here we are. We've got, these are the different things that we can set up. And you'll notice by default, it's in free running mode. So we don't actually set these, but in actual fact, that's the mode that it's in. And we could cause an analog comparison to start an analog to digital conversion, or we could use an external interrupt pin to start an analog to digital conversion, or we've got these different options here in timers. So now, again, just having a look at the pictorial on this will show how I've used one of the timers to create an ADC, okay, conversion. Let's go down here, the interrupt flag. So now we're talking about when the conversion is complete, okay? And when it is complete, it sets this flag. Now, it doesn't have to be interrupt enabled to set this flag. It says here this bit is set when an ADC conversion completes and the data registers are updated. So we know that the new value has been written into the ADCH and ADCL registers. So just going back to our diagram, right, of the ADC itself. So once the conversion here has finished, it will write its values into here, and then you can read them, okay, using your software. So once it has finished the conversion and written those values, it will set this flag, okay? Now that's another way that you can tell when an ADC conversion is complete. So you could read this bit here to see if it's still 1, and when it goes to 0, you can know that the conversion is completed. Or here, when this bit is set, the conversion is complete. So you could do either of those 2 choices. Okay. Now, if you're going to use this one, then what you really need to do is you need to clear it when you have read it. So that's what it's saying here. ADIF is cleared by writing a logical 1 to the flag. So it's a little bit funny. It goes high when the conversion is complete. And to clear it, you have to write it to a 1 value. So this is just a little bit tricky to follow here. Just again, if you're going to play with these things in the analog to digital conversion, you really need to delve deeply into the data sheet and do some understanding around it. So don't make any assumptions about these things. Read thoroughly. Now, of course, this flag will be set anytime a conversion is complete. It doesn't have to be interrupt options. So any one of these options in the modes here will cause the flag to be set, okay? But if you want an interrupt to be enabled, you have to set this flag. When this bit is written to 1 and the I bit in status register is set, so that's using this macro function SEI, then this will cause an interrupt to be triggered. So you can see there's all these different options. And if you're going to play with it, so yes, we can have it free running, we can have it single, we can have it triggered by an external source, we can get it to cause an interrupt when it's occurred. So there's all sorts of different things and ways you can go about solving your problem using microcontrollers. It's a great bag of tricks in here for you to play with, okay, when you're trying to solve a problem. So let's have a look at an example. What I've got here is I've got a force sensitive resistor, okay? And now, actually, just before then, if I wanted to trigger an ADC conversion to start on timer counter 0 overflow, then I would look at here, I'd say I'm looking at timer counter 0 overflow. Timer counter 0 overflow is this line. I just have to set this bit here. Okay, so that's that. Okay, cool. Again, if you're going to change these options during the program, then you would have to clear the other 2 bits as well, because you wouldn't want to assume the state that they're in, okay? So let's have a look at an example. I've got this force sensitive resistor and I've attached it to an ATtiny 85, which is just a little version of the microcontroller. I'll show you the actual board in a second. And an FSR is a force sensitive resistor. They're about, this one is about 13 millimeters in diameter. They come as long strips. They come as big square pads. There's all sorts of different versions of FSRs. And basically it's sort of a bit of a log graph here. Looks almost straight line, but it's a bit wonky in places. But this is from here to about here is more or less a straight line of a log graph, okay? So what this means is that if I stick it into a voltage divider, and then I can just see what the values are coming out of it when I put a bit of pressure on it. So I put it into this voltage divider here, and this is the actual FSR value. So my FSR value is going to go down in resistance when I put more pressure on it. Okay, so my force goes up. As my force goes up, the resistance comes down. Okay, so for instance, at 1,000 grams of force, I reckon we've got about 1.5 k ohms of resistance. So if I've got a low volt, if I've got 5 volts here, which is what I'm saying, we've got 5 volts in, and then I've got a 10k resistor here, and I've got 1k5 here, then actually I'm going to have 0.65 volts out. Now I'm going to stick that into my ADC, and just before we just rush in and think of this as a simple formula. It's not. It's a model for a particular specific device, and that's why some of these values here max out at 1023, right? So the voltage is too high. It's too high compared to our voltage reference. And now the AT Tiny 85 that I've used has an internal voltage reference of 2.56 volts. Now that is different to the AT Mega 328P, which has an internal voltage reference of 1.1 volts, okay? So if I was using an AT Mega 328P, then this 1.43 would also exceed the internal voltage reference. Okay, if it was a 1.1 volt internal voltage reference. So I would get 1023 out of here as well. So you can see these values here are calculated with this force sensitive resistor in this position of the voltage divider. So you just thinking, if you swap this around, what would the effect be? And you can do this calculations yourself and then put them into the ADC model, and then you'll find that the values coming out will or will not make sense to you and your application, okay? So again, playing with these different ideas is really crucial. What's going to work and what's not going to work. So let's just have a look at the actual board. I've got one sitting here. I'm going to go off, put this down here at my board, and I'm going to stop sharing the screen so you can see this. And I should be recording from the main thing. I'll just focus this device. There we go. So what I've got is I've got this force sensitive resistor, and I've got and I'm going to put my finger on it, and I'm just going to put a bit of pressure on it. Okay, and as I press on it, you can see the LEDs change. So no pressure is yellow, a little bit of pressure is green, a bit more pressure is this orange, and then max pressure is this red LED. Okay, I've got to be pressing it really hard to get it to go on there. Okay, and you can see there's a very simple little board with this AT Tiny 85 on it. Cool little device. Okay, but I just want to show you this analog to digital conversion with the voltage divider, with an FSR and the voltage divider. Okay, so let's go back to sharing screen again. And what we'll do is we'll put the camera back up here, and we'll go back on to the recording. So now we're looking at what's going on here in this. So let's have a look at the code, okay? And I want to just point out some differences in this code, just to show you that we do things subtly differently, perhaps on a different microcontroller. Now that board I had didn't have a crystal. Okay, all of these AVRs have internal oscillators you can use, and I've got it set up to be an 8 megahertz oscillator. Okay, so in this case I'm using 8 megahertz, and it's coming on from an internal oscillator in the microcontroller. I've got my LEDs configured. These are just some port Bs. This little AT Tiny 85 only has port B. Okay, it doesn't have port A C or D or F or G. It's just got port B, and of course it's only got about 5 pins, so that makes it useful for a few little things, but not everything. Now I've got my FSR, I've got it connected to ADC channel 2. Okay, so ADC channel 2 is it's pin B.4 actually of our microcontroller. It's not B.2 or anything like that. So you've got to look at us up in the data sheet. I'm not expecting you to, in this course, work outside the realms of the ATmega328 data sheet, okay? This is just to go over you that this information applies to all of these AVRs. You want a small one to do a little job, you want a big one to do a more complex job, okay? You've got all these different options. I've written a little function here to turn off all the LEDs. Of course, all the LEDs are on port B0 to port B3, so I can just turn them all off by forcing those 4 bits to 0. Okay, simple LEDs off. And then I'm setting up, because I've got an 8 megahertz, I can set up my prescaler to 64, which we've already worked out in a previous example that, well, if I had a 10 megahertz crystal and I divide by 64, I get 156 kilohertz. So you can figure out that actually 8 megahertz divided by 64 will give us a frequency which is in our range that we can use with the microcontroller ADC. So that's fine. I'm using the internal, so I've got to set these 2 bits here to get the internal voltage reference. Again, this is not the ATmega328P. It's the AT-Tiny85. It has a 2.56 volt internal reference. Okay. Then I turn on the ADC and I start my initial conversion. There you go. That's cool. Now let's see, what else have I put here? Now what I've done here is I have configured this bit ADLAR, okay, and this makes it left adjusted. So I want to go over this left adjusted thing, and this is really important. Let's go back to our ADC and have a look at our register bits. Now it's in ADCSRA, ADLAR. Oh no, I've made a mistake. It is in ADCSRB. No, it's not. Where is it? Oh, it's an 80 mux. That's where it is. It's an 80 mux. Let me just go back to my notes and just make sure I put 80 mux there. I didn't. Okay. So AD mux. Double checking my data sheet all the time for my absolute reference. Okay, for what I'm doing. So now let's go back to the data sheet and think about this ADLAR bit. Okay. So there's our mux. Lookups for our different bits, and we're going to find out where we're using ADLAR. Okay, ADCH and ADCL. These are our 2 bytes coming out of our data conversion. So it's a 10-bit conversion, which means that the lower 8 bits are in ADCL. So these are the lower 8 bits of our conversion. And these here are the upper 2 bits of our conversion, okay? So this is how we read it, okay? The numbers coming out will go from 0 to 1023. Now we can set this bit, ADLAR1, and what it does is it does a 10-bit conversion again for us, but it left adjusts the conversion so that what we're getting out of it is the most significant 8 bits are now in the ADCH register, and the 2 least significant bits are in the ADCL register, and these bits here are unused. Okay, so what that's doing is, instead of having it right adjusted, which is usual for a number, so that all these leading bits are 0, what we've done is we've left adjusted it, and so all of the trailing bits are 0. Now, the advantage of doing that is that we can just read these 8 bits here and ignore these 2 bits here. And the purpose of doing that is we can actually do faster conversions. We can up our clock rate to beyond the 250 kilohertz, because we're not worried about these 2 bits and the final couple of stages of the conversion. We're interested in these bits here. Okay, So what I've done in this situation is I have left adjusted the result, and I'm only going to read this register here. Okay, I'm just going to read the high register. So let's see how that works in my code. So what I've got here is I am going to, now I've set it up here to, and this is really important, to left adjust the conversion into ADCH. Okay, so that's left adjusting the conversion. So most of the digits will be in the high channel, in the high byte of the ADC. Now, I've just purposely put a little note in here. I often don't put this in, but I put this in just to say the fact that because we're not setting any bits here, it will be in the single conversion mode. Okay, just because it's not there doesn't mean to say that it's not in any mode. So this by default, it goes into single conversion mode on power up, and all these bits are cleared. Now, what I'm going to do down here in the code is I'm going to make all my pins initially as outputs. And this is a bit different to how I might do it normally. I might only do outputs as when I want them to be in pins to be outputs. But in this case, I've made all of them outputs, and I'm just making this one here an input. Okay, just a shortcut way of doing it around the other way. Now, what I'm going to do is I'm going to declare an 8-bit value. Now, normally, of course, we would be reading numbers from 0 to 1023. But in this situation, what I'm doing is I'm only reading 1 byte, the high byte, which has got everything left adjusted into it. So I'm just going to read that. And therefore, I'm only going to read 8 bits. That's why I'm doing that. So when we come down here and we actually do the read ADC bit, the read ADC function, we'll go to this function. Again, it only returns an 8-bit value. And now what we're doing is we might clear, this is standard, we clear any previously read channel, and we set the new conversion, the new channel for the conversion. Okay, and now what we're going to do is we're going to start the conversion. Okay, this starts the conversion. And then what we're going to do is we're going to wait for the conversion to be complete. And you can see that I've purposefully highlighted the semicolon here. Now, again, I've talked about this in terms of good practice about writing software, and it's unclear in this situation what that means. So I would normally actually at least do this, because that there would actually would make it really clear that it's actually a blocking piece of code. So we're waiting for this to change, this bit to change, so that we can go on. So while this bit, okay, we wait until the conversion is done. And then we return just the high 8 bits. So we've left adjusted it. So its number will be from 0 to 255, okay, coming out of this. And then what I do, okay, so I've got this value, I've read it here, and in the next line, what I do is I right shift it by 6 bits. So instead of having an 8-bit number, I've now only got a 2-bit number, okay? So I've only got 2 bits coming out of this. So just make that really clear again. I've read all 8 bits from the high register, and then what I've done is I have right shifted it by 6 just to get only the most 2 significant bits. And then what I'm doing is these 2 significant bits will be, now I've pushed them back to the right hand side, and what we've got there is we've got 4 options. We can have 0, 1, 2, or 3, okay? And that's what I'm doing to set a particular LED. So to turn on the LED, I've got to have it's got to be pretty heavily pressed to get this LED to come on, and a light bit of pressure, no pressure will turn this one on, and a light bit of pressure will turn this one on. Okay, so this is how you might play with this. And I just want to, oops, I clicked the wrong button there. Let's go back to this again. I just want to go over again the conversion process that's taking place here, because it's just a little bit complex. Okay, so let's have a think about this. I'm going to get a piece of paper out here and just explain what is going on with this conversion and these 2 bytes, and then left adjusting it and then right shifting it, just so you get this really clear in your own mind. So we'll stop the share and we'll get the camera to work. Right, so I'll put the camera down on my piece of paper. My piece of paper is upside down, so I just need to twiddle the settings on my, there we go. Change these settings, and I'll just focus that. Okay, get a bit more light on the subject. Right. Yeah. Okay, so what do we got? What do we got? We've got, usually what we have is we have a 10-bit conversion. So we have a 10-bit conversion, which actually must be stored in 2 registers. So we've got ADC L and ADC high. So say the conversion is the number 754. 754. Well, you can tell that it exceeds 255. So some of these bits here must be set. And because it's only a 10-bit conversion, you know, we've got 8 bits there, and we've got 2 bits here. We know since it's 754, some of these bits must be set. So this is when ADLAR equals 0. So that's the default situation. Now what I'm going to do is I'm going to set to ADLAR to 1. So that's this situation here. Now ADLAR is set to 1. And what I'm going to do with my conversion now is that our number of 754 will actually be in these bits here. Okay, so we actually left adjust it. So that's what, you know, we're doing, we're left adjusting it. And so this is still ADC high, and this is ADC low. Now in my function, I'm only returning, from my function, I'm only returning this. Okay, I'm only returning ADCW. Sorry, ADCH, not W, it's the whole thing. ADCH. So I'm just returning those 8 bits there. And so what I'm doing is I'm reading it into a value. I called it FSR value 1. So it's an 8-bit number, and this has all gone into the 8 bits. Okay, so I've got all 8 bits. Right. So now what I'm going to do is then I'm going to go FSR val, and I'm going to right shift it by 6. So what that means is that FSR val, this register here, these 2 bits here all move along. Everything moves along, but of course these bits here all fall off the end, and we lose them all, and only those 2 bits go into here. So let's have a look at an exact number. Okay, I'm just going to open up my little calculator on the computer and put some exact number in. This number is 754. So you won't be able to see this, but I'm just going to use the calculator in Windows. I'm going to go into the programmer mode, and I'm going to enter the number 754. And now in binary, 754, and whoops, there's my red pen, that's what I'm looking for. So 754 has the value 10111110. So instead of returning this number here, what I'm going to do is I'm going to left shift it, left adjust it, so that this becomes 10111110. So as you can see, I'm just left adjusting it so that it's all filling up this part of it. And then what I'm doing is I'm only returning these values here. So I'm just returning 10111100, right? And then what I'm doing is I'm pushing it right 6 times. So these 2 bits here end up here, and these just all disappear because they differ. So I end up with that. Right. Now, I want to ask you a really silly question. Well, actually, it's not a silly question. I've done something very long-winded, haven't I? Because what you can see is actually all I wanted was these 2 bits here in the first place. Okay, so if I didn't left adjust it and I just returned that, then that's what I would have had down here. Okay, so just when you're thinking about why you're doing this, and of course I've done this in this situation just to show what's going on. So I'll just go back to sharing that screen again. So back here we are again looking at what's going on and thinking, let me just play with my screen because you can see that it looks upside down when I'm doing this. Where's my adjustment for the screen? There we go. Video settings. Let's just rotate that again. There we go. So now I'm back in the screen again. So looking at the code, you can see I've done quite a long-winded process here to get these 2 bits that we can check for our LED. I could have done something much simpler, okay? And so right, I just use this as a talking point for about what this code is doing and trying to help you pick it apart. So we could do away with this line. There's no need to actually left adjust it. And then what we could do is we could return just ADCH, of course, and ADCH, then we would not have to do this right shift. Okay, so there's an interesting little explanation of an example around ADC. Yes, it's complex, and it's more complex than really you need to be working at perhaps in the course at the moment, but it's there to show you just to think about all the implications of what could happen with analog to digital conversion. And of course, looking at the questions in the assignment, they'll help you understand how to do this. Nothing at this level of this particular example. What they'll also do is the pictorials will really help you as well. So I hope this has been useful information about analog to digital conversion. And that's the end of the ADC topic. Cheers.